So this is a teaching video on analyzing functions. We'll begin by just talking about the parents of the analyzed functions, and the two parent functions are y equals 1 over x, y equals 1 over x squared. So we can learn a lot from them because we already know what they look like. They have a this one looks, sorry, you can hear my family singing in the background. So this is what y equals 1 over x looks like, if you remember, and this is what y equals 1 over x squared looks like. And so the key thing, the things we notice is both of them have a vertical asymptote and a horizontal asymptote, and they so that means there's a discontinuity which at the vertical asymptote. Now what these don't have is holes, and you can't have holes in a rational function, so we'll get to what makes something a hole. But for right now, let's talk about the asymptote. So notice about 1 equals 1 over x, the asymptote is at 0, and notice that's what makes the bottom of the fraction 0. So in other words, 0 is a root of the denominator of this fraction. Same thing over here. 0 is a root of this fraction. But the difference is, in here, 0 is a root with multiplicity 1. And over here, it has a multiplicity of 2, doesn't it? Because 0 occurs twice as a root. And notice the difference between the vertical asymptotes. So here there's a vertical asymptote, and the behavior on either side of the asymptote, on the left side it's going down, on the right side it's going up, or more importantly, it's doing something different. So over here, notice again, well, I didn't draw that very well, did I? Has an asymptote in the same place, but the behavior on either side of the asymptote is the same. Here it's different, there is the same. By behavior, I mean what is the graph doing as it gets close to the asymptote. So here, as I get close to the asymptote on one side, it's going towards negative infinity. As I get close to asymptote on the other side, it's going to positive infinity. Over here, they're both going to positive infinity. And you guys know that if I put a negative in front of here, that would just make them both go down, right? Or if I put a negative in front of here, that would make this one go down and this one go up. So, so that's, we draw from that. So if we see something like this, like y equals 1 over x minus 2 times x plus 1, so that is also a rational function that's going to have an asymptote or 2. And so we can look at this and say, well, the asymptotes occur when the bottom of the fraction is 0, or the roots of the bottom. Okay, so so this one is going to have, so it has, the roots of the bottom are 2 and negative 1. So that means at negative 1 and 2, I am going to have a vertical asymptote. And so we can establish real quickly where the vertical asymptotes are. Now, the difference would be, since both of these have a multiplicity 1, then we know that behavior on either side of the asymptote is the same. Is different, because it has a multiplicity 1. If this had a square next to it, it wouldn't change where the asymptotes are, but it would mean that the behavior on either side of the asymptote is the same, meaning they're either both going up or both going down at negative 1, because that's the 0 that produces that asymptote. Okay, so that's the idea of asymptotes. Now, the other thing we notice about this is, notice that these guys never cross the x-axis. Why is that? Well, remember, the way we find x-intercepts is by making the y equal to 0 and solving for x. So notice in both of these fractions, if you let y equal 0, well, there's no way to get that, because the way you make a fraction equal to 0 is by making the top equal to 0. And there's no way to make the top of this fraction equal to 0. And that's why there's no x-intercepts. if we would have had a, well, if we have like a, in this case, the same is true. There is no, it never crosses the x-axis. So now if we would have had like an x on top and an x minus 2, x plus 1 squared, well, that would cross the x-axis at 0, wouldn't it? So that means it would cross right here. Okay, so we can tell a lot about a function just by finding out where its asymptotes are and where its x-intercepts are. And we find x-intercepts the same way we always have, by studying y equals 0 and solving. But the cool thing about rational functions is when we're trying to make y equal to 0, we only have to look at the top, right? Because if the top is 0, it doesn't really matter what the bottom is as long as it's not 0. And we'll talk about that in a minute, okay? So if the top is 0 and the bottom isn't, it's an x-intercept. If the bottom is 0 and the top isn't, then it's a vertical asymptote. Okay? Okay. So now, what happens if we have a situation like this, where it's y equals x times x minus 2 over x minus 2 times x plus 1 squared? Okay, so now we have the roots of the top are 0 and 2, and the roots of the bottom are 2 and negative 1, with a multiplicity of 2 on negative 1. So notice that we have a root on top of 2 and a root on the bottom of 2. Okay, so what I said earlier was, if it makes the top 0 and doesn't make the bottom 0, then it's an x-intercept. If it makes the bottom 0 and doesn't make the top 0, then it's a vertical asymptote. So what happens if it makes the top 0 and the bottom 0? So and that's the case we have here with the 2's. 2 is a 0 at the top and a 0 at the bottom. So in that case, we have what is called a hole. Okay, because notice, and this is why it's a hole. Notice that I can kind of, and those of you that have me for 140, we made a big deal about this throughout 140. I can kind of cancel out x minus 2. And the reason why I say kind of is because if I plug in any number for x, it's going to be, this right here is just going to be 1, right? Because if I plug a 3 in for x, I get 1 over 1. If I plug a 4 in for x, I get 2 over 2. If I plug a 5 in for x, I get 3 over 3. So it would cancel out because it's 1 everywhere except for at 2. When I plug in a 2 for x, I get 0 over 0, which cannot cancel out. 0 over 0 is not equal to 1. So there's something funky going on when x equals 2. Okay, so let's put all that together and sketch a quick graph of this. Okay, so we said that there's an x-intercept at 0. We said that there's a vertical asymptote at negative 1. And we said there's a hole at 2. Okay? So, now we can put the x-intercept in, no problem. We can put the vertical asymptote in, no problem, because we know what that looks like. Now the hole, we don't know exactly where it is. We just know there's a hole somewhere. Okay? So then my next step is to figure out where that hole is. So now remember, the way a hole works is the graph comes up to it and just hops over it and then keeps going, right? So what we're going to do is find out what's happening as it gets close to that hole. So basically what we're going to do is take the limit of this function as it approaches 2. And what happens when you take a limit is, so here, we'll hop over here and say, what's the limit as x approaches 2 of x times x minus 2 over x minus 2 times x plus 1 squared. So if I take the limit of that, so that means x is approaching 2. So what this means is I'm asking what happens here, what happens to this expression as x approaches 2. Not when x equals 2, but as x approaches 2. This is the same kind of terminology we use when we talk about in behavior. Okay? So as x approaches 2, that means that x isn't 2, so we can cancel this out. So what we're really trying to find is the limit as x approaches 2 of x over x plus 1 squared. So as x approaches 2, notice that this is getting closer and closer to 2, and this is getting closer and closer to 9, isn't it? Because if I plug a 2 in there, I mean, I know that's what it's. If I put in something smaller than 2, it'll be a little bit less than 3. If I put in something bigger than 2, it'll be a little bit more than 3. So this is getting close to 9, and same thing up here, this is getting close to 2. So what that means is that the whole is found at, what was it, 2? 2 comma 2/9. Okay? So then I go over here and go over 2 up 2/9, which would be very big, which is a little hole right, right about there. Okay, we're getting close. All right. So now, if we want to find out what's going on, really the final step is to figure out the end behavior and figure out where it's above and below the x-axis. So when I'm talking about end behavior, this is probably the hardest function to deal with end behavior on, because you know, a lot of the end behavior we've done so far, you guys know how the polynomials work. We've talked about that. So we don't. We need to figure out what is it doing as x gets bigger and bigger positive, and as x gets bigger and bigger negative. So once again, we're going to use this limit process where we're going to say the limit as x approaches 2 of x times x minus 2 over x minus 2 times x plus 1 squared. I'm sorry, not as x approaches 2. We want to do as x approaches infinity. Okay, so here's the way you think about it. As x gets bigger and bigger, notice that really on top what we have is the highest power is x squared, and the smallest power, or the biggest power on the bottom, is x cubed. Do you buy that? So as x gets bigger and bigger, the highest power becomes dominant and the other things become less important. So essentially, this thing is growing like x squared over x cubed. And since x cubed grows a lot faster than x squared, that means the bottom is getting big faster than the top. And what happens to a fraction when the bottom gets big? The overall fraction gets smaller. So this thing, the limit of this thing as x gets really big, is going to be 0. In other words, the bigger x gets, the closer this expression gets to 0. So that means that this thing has a horizontal asymptote at y equals 0. So now that tells us, since we're above here, this thing must be coming down like that, right? And getting closer and closer to 0. We also have a crossing right here. So that means this thing must cross right there. And we know it doesn't cross anywhere else because there isn't any other x-intercepts. So that means it must be headed down from here. Because when we're talking about, when we get close to the vertical asymptote, there's only one of 2 ways it can go. It either goes way up or way down. I mean, it either goes to positive infinity or negative infinity. So it has to be going down towards negative infinity, because if it turned around and went up to positive infinity, it would cross the x-axis right there, and it would show up as an x-intercept. Okay? Now, because, as we talked about earlier, because -1, the root that produced this asymptote, has a multiplicity of 2, that means the behavior on either side of the asymptote is the same. So then we know that this thing is also looking like this. And it also doesn't cross the x-axis because there's no other x-intercepts. So that means it must be approaching the x-axis like this, because we know there's a horizontal asymptote here. Now, and so that is the function. If you want to throw this in your graphing calculator and check it, that's essentially what it looks like. Now, the graphing calculator won't show the whole because the pixels are just too small, but that's essentially what it'll look like. Now, notice some of you might be thinking, wait a minute, we crossed the horizontal asymptote here. Yes, we did cross the horizontal asymptote, but that's okay. Vertical asymptotes you never cross. Horizontal asymptotes you can cross, but in fact often, or it's not uncommon to cross them towards the middle of the graph. So horizontal asymptotes are really just something that show up as you look way out to the right or way out to the left. So we have a lot of graphs that that might do all kinds of crazy stuff in the middle, but then eventually they head towards a horizontal asymptote. So in here they might be doing this, but if you look way out to the sides, you can see the horizontal asymptote. That's different than vertical asymptotes. Vertical asymptotes are lines that the graph just does not cross. Okay? All right, so that's a quick initial hit on rational functions. I'm going to make a separate video on the end behavior because I just hit one of the cases that just end behavior for this one, but I'm going to do a video that's just strictly on how do you determine the end behavior of a rational function. All right.